All right. So let me say, make an observation about, I think these are called Cayley tables, the multiplication tables. Let me call, a simple theorem. Permutation groups are very, the symmetric groups are very, very powerful. And because of this theorem. I'm not going to quote unquote prove the theorem because I think it's kind of almost like obvious, but you're welcome to try to do it. Okay. So suppose that, let's start, with a simple observation. About a finite group, finite groups, multiplication table. So what do I mean by that? So if I have a multiplication table like this, so we have E, A, B, C, D, dot, 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 E, A, B, C, D, dot, dot, dot. Then we're going to have E here, A squared, B squared, C squared, D squared. Here we'll have A, B, C, D, A, B, C, D. Here we will have B, A, then B, C, B, D. Here we'll have A, B, A, C, A, D. Here we'll have C, A, C, B, and then C, D. Here we'll have D, A, D, B, D, C. Okay, you get the idea. Now, I'm going to make a statement that, simple observation, that no two rows or columns, for that matter, of this table are identical. Okay, so when they all have the same, same elements, but they are shuffled and their ordering is different, right? So how do we prove this? Of course, we use our favorite technique, which is reductio ad absurdum. So to prove this, assume, to prove the statement, assume, assume otherwise. So for example, like from, say, the A row, so which is the A row? A row is this one, right? This is the A row, okay? So from A row, let us choose two elements which are supposed to be identical. Now let us choose two elements which are identical. And suppose that they, suppose they occur in the M and N columns. Then those elements are AM and AN by definition, right? But by the group, by the inverse, postulate, A inverse A of M, A inverse A of N gives us N, M is equals to N. So we see that M and N are the same column, which means that AM, which means that they're not they're not from different columns, right? So that contradicts our initial assumption that the two different elements were equal. Okay. So, our assumption was that M is not equals to N, but we saw that just M must be equal to N. Okay, so this is shows us that every row or column is unique, the arrangement. So what does this mean? So this implies that any column or row in the multiplication table is a unique permutation of any column or row. So this way of thinking about it shows that any finite group is a subgroup of some symmetric groups. Okay, some symmetric group. And this is known as Cayley's theorem. Okay. So this is a very, very powerful observation, is that because every row or column is unique, is a unique permutation. So that means that the action of, because it's the action, the multiplication on elements that give you the different rows or different columns, right? So those actions can then be thought of as a permutation on the elements. It's kind of an automorphism. And because the resulting element is a unique permutation, and it must be part of some permutation group, that action. And therefore, we decide that any finite group is a subgroup of some symmetric group. Okay? Do we have any questions? I mean, this is a very non-trivial thing. I mean, so, like for example, you can think of these guys as some initial set of objects, right? And then multiplication by A, shifts them around. So multiplication by A is a permutation of the original objects, right? So, and multiplication by B is another permutation, right? And so we see that because each row is different, that going from one row to another is a unique permutation. And therefore, we can think of this multiplication table as being a subset of the multiplication table of the set of some symmetric group. Okay, it may be I don't know much about how you embed it. I mean, there might be some embedding theorems, and that'll take us too far away from the aim of this course. But this is a good reason to kind of this shows that the symmetric groups are they are basically a catch-all category when it comes to finite groups.
Can you please explain that part where you said every finite group is a part of symmetric group or something like this?
Okay, I will, but I have a question first, so let's ask Nahi what he's trying to say.
Sir, in this sense, like any finite group is a permutation group, right? Because
exactly.
Yeah.
Any finite group is isomorphic to a permutation group, yes. And Farhan, your question was?
You said something like every finite group is a part of symmetric group. So could you please explain that?
So you see that what we have proved here, that every column here, sorry, row here is unique, right?
Yes, sir.
So another way of saying that would be every row is a unique permutation of the first row.
Yes, sir.
Right? So each of these elements can be thought of as a permutation of the first row.
Yes, sir.
And therefore we say that all the elements together of any finite group form a subgroup of some symmetric group. That is, it is some permutation group.
Oh, okay, got it.
Okay. Right. Any other questions or comments?